All right, so questions. I'm all right. Thank you. How are you? Acceptable. It's Friday. What's week 7 Friday?
I'm acceptable by Friday standards.
Yeah.
It's better than the rest of the week, acceptable.
So questions?
What would be a good way to start ODP 241?
To start,
What a good way to go along with how it works?
to complete your hours of work you've already done on it.
Oh, of course.
Yeah. So, ODP 241, I'm giving you a try, right? I'm giving you the root of a structure that already exists, already has stuff stored in it. So you really kind of want to do some kind of loop. Right, from 0 up through the string length. So this gets you each character in the word. If the pointer for that character is null, you're done. Word's not in the try. So go through your input word character by character. If the pointer corresponding to a letter is null, just return 0. Don't have to do anything more, don't want to do anything more. Okay? Otherwise, move to that node and repeat. So here's your root. Make yourself a trinode pointer. Let's call it temp maybe, which points to that node. Take the first letter of your word, see if the pointer is null. If it is, return 0. If not, set temp equal to whatever that's pointing to. So it's kind of like when you're following along in a linked list, right? If the next field is not null, you set temp equal to temp arrow next. Well, same thing. If temp arrow letters bracket I is not null, set temp equal to temp arrow letters bracket I. Right? That's the next node of your try. And then go back and find your next letter. Figure out the index of that and see if temp arrow letters bracket that index is null. And if it's not, set temp equal to that. As you do this, you're moving down that try page that you filled out earlier in the week. And for each letter, temp is pointing to that next node. And after your last letter, you follow that link. Temp should be pointing to that last try node that should have end of string set to 1. So if you make it through this loop without returning 0, now you just want to see if temp's end of string is equal to 1. And if it is, you found your word, return 1, otherwise return 0. So my suggestion would be take that worksheet that you had that you were filling out the try structure for, or make one, right, with some small words in it, and write some code to try to do what you do on paper, right? First figure out on paper, how do I figure out if there's a cat in my structure, right? Go over to the C, follow that, find an A is null, there's no cat, right? Do it for a dog, you find that there's a dog in there, right? And then just structure your loop to basically do what you're doing on paper. Yeah?
So, do you have a particular reason why you chose a for loop for this?
No.
Okay.
I always do for loops. But you could do while word bracket I is not \0.
For loop is kind of easy to break it out of loop, so we can limit the size to small as string is.
Mm-hmm. While loop is nice because you don't need string.
While loop we will need a flag to break it.
Or you can just break. Well, I mean, the only reason to break out of this loop is if you find that you can't follow your links anymore, in which case you just want to return. So that breaks out of a for loop or a while loop equally well.
Yeah, inside of something for loop, we have I as index, we use for index.
Yeah.
While we have to declare another one.
Right, you got to remember to increment it, which I always forget. So, yeah.
Yeah, I can't visualize properly on how it's brought off the second person run the function.
Mm-hmm.
But when you do temp equals to letter or word, however it is, bracket I, and every you update it, I know that's updating to the next letter, but how does that look like in terms of when you run it through and it doesn't
So let's make a bit of a try here. So here's our root, which I'm also going to call temp. And so here's the D, and that points to another node, and there's an O, and it points to another word, and there's a G, and it points to another node with end of string set to 1. All right, and your word equals DOG. All right, so what do? We go through each letter of this. We start off with temp being the root. Grab the first letter, right? Subtract an A from it. So that gives you a 3. So look at temp letters, bracket 3, but use a formula, word bracket I minus A, right? So I can just say set temp equal to that. And now one of two things will happen. Either temp is pointing here or temp is null. Right, so this was ODP 240. Take the first character and find the pointer that corresponds to that letter. So if I set temp equal to that, if temp equals null, then it's not found. Otherwise, temp is pointing to the second node. Go back to the top of your loop, grab your second letter, find the index, and now do the same thing. Temp equals temp letters, second character minus A, right? And that's going to be the pointer that's stored here. So after I do this assignment statement, now temp is either null or it's pointing to the node that corresponds to the third letter. Right? So if temp is null, then it's not found. Otherwise, I'll go on to the G. Do G minus letter A, that's going to give me a 7. I'll look at temp letters bracket 7, and when I set temp equal to that, temp will be pointing to this last node. If temp's not null, I don't return. I kick out of my loop, and now I know temp should be pointing to this node that should have end of string sets. Now I just see if temp arrow EOS is equal to 1. And if it is, you found a dog. Return a 1, otherwise return a 0. So write some code or some pseudocode, make a cleaner drawing of a try, and test your code, right? Or your algorithm by doing this with different words, and make sure if your word's found, it gets down to where it returns 1. If it's not found, it returns a 0. And then try some other things. Try to see if do is found. Right? With this try structure, do should return a 0. With this, what's going to happen is when I set temp equal to temp arrow letters bracket 13, temp's going to be equal to null. I mean, sorry, it's going to come down here. I'm going to check to see if this node's end of string is 1, and it's not. So it should return a 0. So test your code, tweak your code like that. Okay. It's a little hard to use GDB on these ODPs because you don't know what the main program looks like. But you could build yourself a try if you believe you understand how tries get set up, right? You can build yourself a try in some code. It's a little tricky because now you're trying to debug two programs. Your program to build a try and then your ODP 241 to search your try. But it might actually be helpful to do that because then you can go in GDB and see how the try is set up. All right, or post questions. So other questions on tries? All right, so I made a wish list for the rest of the quarter because we're done with week 7 after today, which means we've only got 3 weeks left, which is insane. So we're going to continue with talking about sorting today, and I want to talk about a merge sort. Which is a nice n log n sort, and it's recursive. I want to talk about heaps and heap sort. I want to talk about something called a quick sort, which is actually pretty quick. I want to talk about a radix sort. I may talk about a topological sort, or I may not. But we'll do this today and probably part of next week. We'll continue talking about sorting. And then I want to talk about dynamic programming. And I'll probably give you some ODPs related to dynamic programming. And dynamic programming is going to be PA5. And it's a different approach to writing recursive functions but speeding them up so that they become tractable, because a lot of recursive functions, a lot of very simple recursive functions will just run forever. They just take too long to get to a solution. Dynamic programming is a nice trick to speed up those situations. So we'll work on some interesting problems in this area, including PA5. And then I want to revisit tree balancing. And look at code for AVL trees, look at red-black trees, maybe look at some other versions of trees. And that should take us pretty close to the end of the term. We'll leave a couple of days for wrap-up. PA5 you're going to present in class since it's a group project, so we'll leave some time for that. And so that'll probably round out the quarter. And then you got an exam and you're done. Alright, so that's where we're heading. Let's talk about merge sort. Merge sort is actually what I do when I'm sorting your homework or exams in this class, because I got 60-some things to alphabetize, and that's a lot. I think normally I do an insertion sort. So I have a stack of papers that come in whatever order you finish your tests. And I start from the top and I just grab the first one and I put it in my output pile. I grab the second one, I put it before or after the first. I grab the third one, I put it in the right place. So I think I usually do an insertion sort. That's just, before I knew what an insertion sort was, that's how I learned to sort things. But when you have 50 things, 50 exams over here, and you grab one exam, you've got to go through 50 things to figure out where to put this next paper, right? 25 on average. But those last 10 papers, if it takes me 25 comparisons to decide where to put it, that's 250 exams I have to glance at just to put those last 10 exams alphabetically in this stack of 50. So it adds up quickly, right? 60 students, n squared is 3,600. So it's a fairly time-consuming process. So I actually end up doing a version of merge sort. So let me show you the idea of merge sort. So I've got two stacks of cards here. And this stack is much smaller. It's only got, half dozen cards in it. So I go ahead and I sort this, maybe using an insertion sort or something. So this stack is sorted, right? I usually do this because the exams are given in 2 sections. So while the second exam is going on, I sort the first one. And then here's the names from the second class. Okay, and so this stack is also sorted. So I have 2 sorted stacks, and I want to put them together and end up with a full sorted stack. Okay, here's how I can do this with a single pass through this data. I look at the top card on each and I say which one is smallest. Okay, that's an ace. I'm going to put that in my output pile. Now which one is smallest? That's a 2. Which one is smallest? 3. Which one is smallest? 4. Smallest? 5. 6 versus 9. 6. 7 versus 9. 7. 8 versus 9. 8. And at each point, I'm only comparing the top of each input pile. Right? 9 and 10. 9 is smaller. I put 9 onto my output. 10 and 11. I put the 10. 11 and 13. I'll put the 11. 12 and 13. 12. And then nothing versus 13. 13 is smaller. And when you're done, you got everything sorted. So it's a single pass through 2 smaller problem sets. And to make that pass, you simply compare the top entry on each of these 2 piles, and you pick whichever one is smaller in this case, add that to your output. Okay, that's what we call a merge. So assuming we have 2 arrays, roughly n elements each, this basically takes n operations to put these things together. So we can define an algorithm So let's define some pseudocode for this merge sort. And merge sort is going to take an array of n numbers. I'm going to call that array D for data. And we want to sort it using this technique. And don't get too flustered over the details here. I'm going to set A equal to basically the first half of my data. So elements 1 through n over 2. And I'm going to set B equal to the second half of my data. And this is the magic of pseudocode, because I don't have to say how I'm going to do that. But I'm going to split my data into 2 smaller arrays, each roughly half the size. If there's an odd number of elements, they'll have slightly different sizes. That's not a problem. So I create 2 sets, A and B. That's an order n operation, right? Okay, so I'm going to sort A, and then I'm going to sort B, and then I'm going to merge A and B. And I'm done. And I don't really need to copy my data into A and B. I'm just doing that so it's easier to talk about these sets. So split your data into 2 sets, A and B. Sort set A, sort set B, merge them together using this interleaving technique, right? And you're done. And this is basically an order n. The number of steps you have to do is proportional to how many numbers you have in your original data set. So here's the question. How am I going to sort these smaller pieces of data? I have this array A, which is half the size of the original. How should I sort it? What? I'm going to be as lazy as possible. I'm just going to call a sort function. I'm going to call a sort function called merge sort. Alright, so this is hugely recursive. So split your data in half, merge sort each half, and then interleave those two pieces that are sorted into a single output, and you're done. Of course, when I do step 3 and I say merge sort A, what's going to happen is I'm going to call merge sort. That instance of merge sort is going to split A into two pieces. It's going to merge sort each of those and then interleave them. And each of those calls to merge sort will do exactly the same thing. I need a base case. So my base case is if there's only one element, I'm just going to return, because there's nothing to sort. So that will end the recursion. All right, got the basic plan. So let's sort some data. All right, we're going to sort 8 numbers. It's a nice power of 2. So what do? I split into 2 pieces, and I'm going to say sort 10, 4, 7, 6, and then I'm going to sort 8, 3, 2, 5, and then I'm going to interleave, or mix those together. So this is all assuming I originally want to sort these 8 numbers. So I break it into 2 smaller sort problems and I mix the results together. Okay, how do I sort 10, 4, 7, 6? I'm going to split this in half. I'm going to sort 10 and 4. I'm going to sort 7 and 6, and then I'm going to interleave. Yeah,
What if we have very long strings with many numbers?
that's okay. Just keep cutting it in half.
What if that's like number 7 numbers? I have to write and cut by half.
I mean, if it's odd,
Yeah.
make a choice. Do 3 and 4, or 4 and 3. So it's one of the many details you have to take care of in code. Is if your number is not divisible by 2, you gotta put an extra 1 in either the first set or the second set. So, but that's just code. Alright, so how do we sort 10 and 4? Break it into 2 pieces and then interleave. So when I call merge sort on 10, I'm going to say if there's only one element, just return. So the result of sorting 10 is just going to be the number 10. The result of sorting 4 is just going to be the number 4. And now we're going to take these 2 arrays and we're going to do that interleaving thing that I did with the cards, which says I'm going to take the smallest of these and put that in the output first. And then I'm going to take the next smallest of either the 10 or nothing, right, which is just a 10. I'm going to put that in second. And then I'm going to return. So the call to sort 10, 4 is going to return an array of 2 numbers, 4, 10. Same thing when I sort 7, 6. It's going to sort 7, it's going to sort 6, it's going to interleave them. This is going to return 6 followed by 7. And now we're going to interleave those. So we pick the smallest element 0, right, which is a 4. Now we pick the smallest of 6 or 10, that's a 6. Pick the smallest of 10 or 7, that's a 7. Pick the smallest of 10 or nothing, that's a 10. And we're done with this sort of 10, 4, 7, 6. So this is going to return 4, 6, 7, 10. Then the whole thing repeats when we get to our second call, which says sort 8, 3, 2, 5, and this is going to return 2, 3, 5, 8. And then we're going to interleave this number array with that number array. So compare the 2 to the 4, we'll take a 2. Compare the 3 to the 4, we'll take a 3. Compare the 5 to the 4, take the 4. Compare 5 to 6, take the 5. 6 to 8, take the 6. 7 to 8, take the 7. 10 to 8, take the 8. 10 to nothing, take the 10. And that's what our original call to sort's going to return. So the pseudocode is really simple. How do we merge sort an array of data? Split your data in half, merge sort the first half, merge sort the second half, and then interleave. The implementation is always ugly because we have details like what if there's an odd number of things. So you look at how many pieces of data you have. If it's even, you just take, well, let's just embrace the ugliness. So suppose you have n pieces of data. So we want to split into 2 arrays, each having n over 2 pieces of data. So the first one is going to have elements 0, 1, 2, all the way up to n over 2 minus 1. And the second one is going to have n over 2 plus 1, all the way up to n minus 1, because we have this index 0. If n is odd, then we might go 0, 1, 2, up to n over 2, and this is going to be an integer. So let's just think n equals 5. So we can go up to n over 2, and then we could do n plus 1 over 2, n plus 1 over 2 plus 1, up to n minus 1. So if n is 5, this would get us elements 0, 1, and 2, and this would get us elements 3 and 4. So we'd have one extra element in the first array. You do something, right? You could go to n over 2 minus 1, and then n minus 1 over 2 something, to roughly split it in half. And if you're not too worried about efficiency, you can recopy all of your data so that you do something very much like this. Right? We make a new array containing those first elements and a new array containing that second set of elements. And each of these arrays start from 0 and they go up to the number of elements minus 1. And that keeps the rest of your code pretty clean. But if you don't want to be copying a lot of data, you can actually work directly on this array, but you got to remember an offset for your index, and that gets ugly. So there's lots of implementation details. The other really kind of ugly piece is when you do this interleaving. Right, if we want to interleave these, well, you need to kind of know where you are in each of these. I can cross these things out on paper and tell what the top of the pile is, but if we're doing this in code, we need something that, points to the top element of each array. So we have an A index and a B index, and we compare those. B index is smaller, so we'll add that to our output array and increment this. And now A index is smaller, so we add that to our output and increment. And A index is smaller, so we add that and increment. And A index is still smaller, so we add that and increment. And A index is still smaller than B index, so we add that and we increment. But now we need to know that we've incremented beyond the end of A. So we don't want to compare B bracket B index to A bracket A index because there is no A bracket A index. So you're in an edge case here. And if one of these things has gone past the end, then you basically just copy the remainder of your other array into your output. So you got to have ways to do that. But none of those things fundamentally perturb your order of complexity. This inner loop where we're breaking your data into two pieces, where we're interleaving, those are still order n. The merge sort is going to be whatever the order of complexity of a merge sort is, but the size of the data that we're sorting gets smaller and smaller each time. But how many times are we going to recursively call merge sort if you start with a certain amount of data? Say you have 100 numbers, are you going to have to call merge sort 100 times? Does it feel logarithmic to you? This is an example of divide and conquer. It's a class of algorithms. We basically take our problem, we break it into smaller problems, we solve those, and then we put the solutions together. And this is what we're going to be doing in dynamic programming, taking a big problem, breaking it into smaller problems, solve the smaller ones, put their solutions together. And this is classic divide and conquer, right? We want to sort 1,000,000 numbers. Well, I'm just going to sort 500,000 numbers a couple of times. And I'm going to put those solutions together in an order n, really simple to do process, and I'm done. Right? So find your friend who only sorts things up to 500,000 numbers and say, hey, here's 500,000 numbers, sort these for me. But they're actually lazy, so they have a friend who sorts things up to 250,000, and they split their 500,000 into two pieces, and they go to their friend and say, can you sort these 250,000 numbers for me? Right? And that person doesn't actually do any sorting. They go to a friend who can sort 125,000 numbers, and so on. And eventually you get down to somebody who only deals with sorting lists of single numbers. And you give them the number 10 and say, can you sort this for me? And they say, yeah, I'll get back to you tomorrow. And they come back tomorrow and give you a 10, right? So nobody's actually doing a whole lot of work. Right? We just keep splitting the problem into smaller and smaller subproblems. So this turns out to be an n log n sort algorithm, which is a lot better than n squared, especially when n's big. If n is 1,000,000, n squared is 1,000,000 squared, that's 1,000,000,000,000, 10 to the 12th. N log n is 20 times 1,000,000, that's 20 million, versus 1,000,000,000,000. So big payoff in terms of time complexity, and not too bad to code. This also works pretty well with magnetic tape, because you're kind of going through the only work you're actually doing is this interleaving, right? We don't actually do any sorting other than that. We sort a single element and we just return the element, and we interleave two sorted lists, and that's pretty much it. And if you have two tapes of numbers and you want to interleave them and write the output to a third tape, right? This is made for magnetic tape because you're just taking the next number in your list. So you compare the two numbers at the beginning of your tape, whichever one is smaller, copy that to your output, and then move that tape to the next number. And you just move one time from beginning to end of each array, and you're done. So this also works well with linked lists, which are kind of like magnetic tape that way. Easy to go forward, hard to jump to a middle position. So merge sorts are cool. I recommend coding some up just for fun. Yeah, I'll find that another time. There's videos you can find on YouTube that visualize all these different sorts. Sometimes using computer visualization, sometimes using dancers. There's a great bubble sort Hungarian dance troupe that does a bubble sort. And each person has a number, and they do these nice swapping of positions based on their numbers, and It's a cool way to see a bubble sort in action. All right, so questions on merge sort. So try this, right, with a deck of cards or a stack of words or a bunch of numbers or something like that. Get the feel for this. Okay, typically on the exam I'll give you some set of data and ask you to do some kind of sort on it. And maybe we'll do this in class on the board or something. After we've gone through a bunch of different sorts. All right, let's talk about a radix sort. I'm making these up. They don't actually get wider towards the bottom. So here's a set of integers I want to sort. And radix sort works really well with things where you have kind of wide numbers or words, right, where we're thinking them as a sequence of characters rather than actual integers. And I think this is similar to how some of the old 1800 vintage sorting machines worked. The Hollerith machine being the first programmable computer. So how do we do a radix sort? And I gotta make sure I start from the right end. And this is an efficient sort. This borders on order 1 in some sense, as long as we put certain constraints on our data. All right, and take a shot. So, so we work digit by digit. Okay, we start with the rightmost digit. There's about a 20% chance I'm going to be backwards here. We start with the rightmost digit, and we sort according to that digit. So we've only got 10 possible digits, and when we sort, we don't want to disturb the order of anything that's already sorted in this digit. So we don't want to do like a bubble sort where we just kind of move things around and we're only getting one number in the right spot. So here's what we're going to do. We're going to make 10 passes through our data. The first pass, we're going to look for anything that has a 0 here. And as we find anything with a 0, we're going to move it into our output pile. Okay, so we go through, there's nothing with a 0. We go through, there's nothing with a 1 or a 2 or a 3 or a 4. So we go through and we look for the 5s. Okay, here's a 5. So we're going to put that in our output. We keep going, here's another 5. So we put that in our output. And we're done. Go through and look for 6s. There's a 6, 4276. There's a 6, 9436. There's a 6, 4176. Go through and look for 7, 777. There's a 7, 9437. That's the end of the 7s. Go through and look for 8s. There's an 8, 9428. And there's no 9s and there's no 10s. Okay, so this was digit 0. Now we're going to do the same thing for digit 1. So we're going to look at this next position. Yeah, I'm pretty sure I'm going to be backwards. Yeah. All right. So scratch the last 90 seconds. Let's start with digit 3. All right, so go through, find all the ones, the zeros, the ones, the twos. Okay, there's a 2, 2115. Find a 3, there's no 3s. Find the 4s, 4276 and 4176. Find any 5, 6, 7, 8. Find the 9s, there's a 9436, 9437, 9428, and 9445. Okay, so now we go on to the next digit from the left. So we're looking at these numbers right here. And we're going to make 10 passes through and move numbers from our input to our output. So this will be D2. So find any zeros, there aren't any. Find any ones, so 2115, 4176. That's it for the ones. Find any 2s, 4276. That's it for the 2s. There's no 3s. Find some 4s, 9436, 9437, 9428, and 9445. All right, now do this for the next digit in. And you got the idea? So digit 1, there's no zeros, there's some 1, so 2115. There's a 2, 9428. There's a 3, 9436, and 9437. There's a 4. There's no 5s, no 6. There's a couple of 7s. Maybe I did it right the first time. So let's look at D0. So 0, 1, 2, 3, 4, there's a 5, and a 9445. There's a 6, and a 4176, and a 4276. And there's a 7, 9437, and a 9428. Yeah, I did it backwards. I was right the first time. But if you flip these around, right, it's sorted.
Right backwards.
Yeah. Okay, so this is a radix sort. And it's order 1 in the sense that if we limit ourselves to, say, 10-digit numbers, we have 10 digits, so we make 10 passes through for each digit, and we have a total of 10 digits. That's 100 passes. And it doesn't matter how many numbers we have, it's always going to take 100 operations to sort your set of data. Well, 100 times n, right? So it's an order n sort. And that's a little peculiar, because we don't really have order n sorts. We have n log n, that's kind of as good as we get. But for n pieces of data, it takes n times the number of digits times the number of possible digits. So if we do this on words and we limit ourselves to 50-letter words, this is order n times 50 times 26, right, which is order n. So it's arguably a very efficient sort, but there's something funny going on in that order n. So we'll do this in the correct order tomorrow, and we'll talk more about the order of complexity, and you'll see that there's actually a log n sneaking in to that constant. All right, so we'll play with that tomorrow. Monday. I'll be in